今天很荣幸，就是说邀请到香港中文大学卓敏信息工程讲座教授杨伟豪老师来给我们做一个报告。就是杨老师是这个世界上非常有名的，就这个信息论编码理论方面的这个专家。我引用网上面的一段话，我查到这个12年的时候，这个杨老师访问清华，那个姚期智教授就说，当时在那个介绍他的时候说杨老师是在亚洲成长起来的享誉世界的知名学者，其成功的学术发展生涯为同学们树立了绝佳的榜样。就是当年在这个清华12年的时候说的。到现在有8年过去了，就是杨老师当然做出了更加杰出的成就，特别是最近刚拿到这个2021年的这个 CUHK， 就说是世界这个电子工程师协会颁发的黑名奖章。我们恭喜这个杨老师，就已经拿了很多奖，现在又拿一个新的奖。然后我们这个交大的话呢，就是说信息学这个我们讲数学学院，就当然我们电子工程学院有很多这个做信息方面的老师，包括陈芳老师是杨老师的学生。那么在我们这个理学院，就是有这个胡国定老师，就是原来是这个他其实是物理系毕业的，然后他其实可以算到我们的理学院里头，他是我们这个中国这个做信息学的这个先驱，特别是他在这个莫斯科大学留学的时候，做了关于 Entropy 的一个很基本的结果，就是和我们今天这个杨老师讲的这个主题是一样的，也是 Entropy。然后后面我们在这个上个世纪大概最后10年的时候，我们这个系主任是叶中行老师，就是这个杨老师在这个康奈尔的这个同门都是跟这个Toby Berger 读的博士所以杨老师我们很有渊源。然后今天杨老师也给我们来科普一下这个 Entropy， 希望我们后面这个学生和老师有更多的人可以跟上这个非常好的一个方向然后我们现在请杨老师给我们做报告，介绍这个 Facets of Entropy。
大家好，非常感谢吴老师的介绍。我今天觉得非常荣幸可以跟大家做一个简单的报告。好，你们听我听得清楚吗？
听得清楚。
好，非常好。
你可以用中文、英文，由您这个
都可以。你想呢，我都可以。
您决定好了。
是不是对上头？
用英文吧，也许有用英文那个对。
Okay, that's all. Okay. Afternoon, everybody. So the title of this talk is Facets of Entropy. Facets means different phases. Okay, so here's some preliminaries. I'm trying to use as few notations as possible, but here just some very simple ones. So I'm going to use n sub n to denote the index set from 1 up to n, and then omega be a collection of n random variables xi from 1 up to n. And here we assume that xi is a discrete random variable. Now, in information theory, we define the entropy as of a distribution like this. And entropy of a random variable x with this distribution px is defined as minus summation x px log px, where the log term can be in any convenient base. And for two random variables, the joint entropy is defined accordingly. So instead of using just px, here I replace it by pxy log pxy, and the summation is overall x and y. Okay, now in information theory, entropy is the measure of uncertainty contained in a discrete random variable. And unlike many other measures, there's a definitive meaning of entropy, which is justified by fundamental coding theorems. So this actually sets entropy apart from most other measures. Now for n random variables, there are 2 to the power n minus 1 joint entropies. For example, when n is equal to 3, we have 7 joint entropies, and these are entropy of x1, x2, and x3. These are the entropies of the individual random variables, and then we have the joint entropies of any 2 random variables. So there are a total of 3 of them. And then finally, we have the joint entropy of the 3 random variables. The reason why there's a -1 here is because we take out the empty set. Okay, so we're going to use the notation x sub alpha to denote the set of random variables xi, where I is in this index set alpha. For example, x subscript the set containing 1, 2, 3 denotes the collection of random variables x1, x2, and x3. So this is a very natural notation. Okay, and we define a function like this. Okay, this is a set function with alpha being the parameter, and omega denotes the particular set of random variables. So x omega of alpha is equal to the entropy of the collection of random variables x sub alpha. For example, we have the collection of random variables denoted by omega, which is x1, x2, and x3. And h omega of this set 1, 2, 3 is assigned to the value, the joint entropy of x1, x2, and x3. Okay, and then we further define, with this setup, we can define a set function, okay? The domain of the function is the power set of the index set from 1 up to n, and we map it to and the range is a real number, okay? Now this is the, this set function, okay, if you input alpha to be any non-empty set, then it will give you the joint entropy of the corresponding collection of random variables. But how about if we input, if we use, we set the parameter to be the empty set. This is, we set alpha to be the empty set. Then we adopt the convention that the function of the value of this function is equal to 0. Okay. Now here, h of omega is called the entropy function of this collection of random variables, omega. Now, it is well known that for any collection of random variables or any joint distribution for n random variables, this entropy function satisfies the following so-called polymetroidal axioms. Now, namely, for any alpha and beta in the which are subsets of the index set, we have h omega empty set is equal to 0. This is by definition. And if alpha is a subset of beta, then the joint entropy of x alpha is less than or equal to the joint entropy of x beta. Okay? And the third axiom is also called the submodular inequality. It says that for any two subset of indices, h omega of alpha plus h omega of beta is greater than or equal to h omega of alpha intersect beta plus h omega alpha union beta. Okay, this is the so-called submodular inequality. So these are well-known properties of the entropy function. Okay, in addition to entropy, we also have conditional entropy defined, written as entropy of x given y, and it can be expressed as a linear combination of the joint entropies. Namely, it is equal to entropy of x comma y minus entropy of y, and mutual information ixy, which is equal to entropy of x plus entropy of y minus entropy of x comma y. And also conditional mutual information, entropy mutual information between x and y conditioning on z is equal to entropy of xz plus entropy of yz minus entropy of xyz minus entropy of z. So all I want to say is that all these information measures can be expressed as linear combinations of the unconditioned joint entropies. So all these four types of information measures, namely entropy, conditional entropy, mutual information, and conditional mutual information, are called Shannon's information measures. Okay, now the polymetroidal axioms are equivalent to the non-negativity of Shannon's information measures. And so what I mean is that all entropies are non-negative, all mutual information are non-negative, all conditional entropies are non-negative, and all conditional entropies, conditional mutual information are non-negative. Okay, these collection of inequalities together actually is equivalent to the polymetroidal axioms that I just showed you in the last slide. Not the last slide, but the few slides before. Okay, maybe this one. Okay, so it's not difficult to show that these two sets of constraints on the entropy bar function are actually equivalent to each other. Okay. So we refer to these four types of inequalities as the basic inequalities. Okay. Now, in a paper published by Nicholas Pippinger, that was in the mid 80s. Now he asked the following questions. Okay. Now these are constraints on the entropies, and we know that in information theory, these constraints on the entropy function actually occupies a central role when it comes to proving converse theorems. So basically, these inequalities on the entropies governs the impossibilities in information theory. Okay? By applying these inequalities, we are able to show that certain things cannot exist in information theory. And for this reason, Pippinger called these the laws of information theory. And he asked whether there exists any constraints on entropies other than those basic inequalities. That is, those constraints that had been known for a long time. Okay, in a paper in 1997, I introduced a region called gamma n star. Okay, it's going to be clear why I want to introduce such a region. Now, maybe I'll take this opportunity to explain to you what I had in mind during that time. I think some of you may be interested. Now, what we usually think in terms of inequality is like this. Okay, so when you think of inequalities, we think of this. We think in terms of some kind of Euclidean space, and then an inequality is usually expressed as kind of like a surface in the Euclidean space. In the case of a linear inequality, it is a hyperplane, and then we have two sides. One side is greater than, and the other side is less than. Okay, so this is the mental picture we have for inequalities. Now, in the situation of all these basic inequalities that I've talked about, now what I had in mind was the following question. So what, when we talk about these basic inequalities, what are the two sides of the inequalities? Okay, one side representing bigger than or equal to, and the other side representing less than or equal to. Okay, so what I want to figure out was geometrically, what are the two sides of these inequalities? What is the right representation of it? Okay, that's the main motivation of this work. Okay, so the setup is the following. We fix n. Now it turns out that fixing n is of paramount importance. If you don't fix n, there's not much you can do. Okay, now you fix n, and for each collection of random variables omega, each omega defines a vector in the to the power n minus 1 Euclidean space. Okay, and we call this the entropy space. Okay, so the idea is that for any collection of n random variables, or equivalently the joint entropy, you just compute the 2 to the power n minus 1 joint entropies, and then you and then you plot a point in the Euclidean space accordingly. Okay. So Hn is called the entropy space for n random variables. This is just just to facilitate this discussion. I don't want to refer to this as r to the power n minus 1 all the time. And just call this the entropy space for n random variables. Okay. Now a vector which is in this Euclidean space is called entropic. if it corresponds to the entropy function of some joint distribution. Okay, so we know that the for a joint distribution, it corresponds to a point in the Euclidean space, and we pick an arbitrary point in the Euclidean space, and we ask whether it corresponds to any joint distribution. If so, we call this point entropic. And then we define this region in the entropy space denoted by gamma n star to be the set of all vectors in the entropy space that is entropic. Okay, so basically what you do is the following. So you have a so this is the Euclidean space, the entropy space, and you for every joint distribution you compute a vector. This is the entropy vector, and then you plot a point there, and then you plot every possible point. You exhaust all possible joint distribution for n random variables, and then you plot all the points, and the union of all these points is the region gamma n star. Okay. All right. So this is the geometric view of an entropy inequality. Just a moment ago, I said that what I had in mind was to come up with a way that you can interpret the so-called two sides of an inequality. Okay, so now we consider an entropy inequality that has the form fh is greater than or equal to 0. Okay, so h is the entropy vector, is a generic point in the entropy space, and f is just some arbitrary function. Okay. Now, in information theory, we say something like this. Okay? For example, entropy of x, y is always greater than or equal to 0. So always greater than. Okay. So what does it mean by always greater than? Always greater than means that it is true for all joint distribution. So to pin down this notion, we actually can express this in terms of this region, gamma n star that I've just defined. Okay, the inequality fh greater than or equal to 0 always holds if and only if this region, which contains all the entropic points in the Euclidean space, is a subset of this region corresponding to the inequality fh greater than or equal to 0. So this is the set of all h such that this inequality is satisfied. Okay. Another way to say this is that the region defined by fh greater than or equal to 0 totally contains this this region gamma n star. Okay. Now, in fact, it's not difficult to see that because we are talking about a non-strict inequality, fh is greater than or equal to 0. This inequality always holds. Again means that it holds for all joint distribution, even only if gamma n star bar, which is the closure of the region gamma n star, is a subset of this region defined by the inequality fh greater than or equal to 0. Okay. Now here I take the closure of gamma n star because we don't know ahead of time whether gamma n star is closed or not. In fact, I'm going to mention that it's actually not closed. Okay, so this is the geometric view of what it means by the inequality fh greater than or equal to 0 always holds. Now this is the set gamma n star, which contains all the entropic points. That is, whatever joint distribution you're talking about, you compute the entropy vector, it will be a point inside this region. Okay. Now this inequality here, fh greater than or equal to 0, is represented by this graph here. Okay. So this side is fh greater than or equal to 0. The other side is fh less than 0. So in this case, fh greater than or equal to 0 always holds, meaning that, well, in this case, we have gamma n star is completely contained in this region fh greater than or equal to 0. So always holds means that whatever joint distribution you come up with, you evaluate the entropy function. It would be a point in this region gamma n star, and because gamma n star is completely contained in fh greater than or equal to 0, this point automatically satisfies the this this inequality fh greater than or equal to 0. Okay, so this is the geometric interpretation of what it means by fh greater than or equal to 0 always holds. Now, on the other hand, this is the other situation. fh greater than or equal to 0 does not always hold. It means that I can come up with a joint distribution such that when I evaluate the entropy vector, it is on the other side of the inequality. So it violates the inequality. That's why we say that it does not always hold. Okay, so this completely captures the meaning of what it means by an inequality always holds or an inequality does not always hold. Okay, and then now we define another region called gamma n, which is the region in the entropy space such that every vector, this is a set of all vectors, such that it satisfies the basic inequalities. That is, all the Shannon's information measures are non-negative. Okay, because we know that the Shannon's all the basic inequalities are satisfied by every joint distribution. We know that by definition, we know immediately that gamma n star, which is the set of all entropic vectors, is a subset of this region gamma n. Okay, and let me show you this picture. So this is the situation. So this is the region inside. The potentially smaller region is gamma n star, and this region gamma n is the region defined by the basic inequalities. Okay, now in particular, an entropy inequality fh greater than or equal to 0 is called a Shannon type inequality if it is implied by the basic inequalities, or gamma n is a subset of this half space defined by fh greater than or equal to 0. Okay, actually this is not here. I don't usually when we talk about Shannon type inequality, we refer to linear inequalities, but it doesn't have to be. So this can be non-linear. It is just the space defined by the region fh greater than or equal to 0. Now, previously we say that an entropy inequality fh greater than or equal to 0 always holds if we have gamma n star being a subset of this region. But now we say that there is a Shannon type inequality if the region gamma n is a subset of the region induced by fh greater than or equal to 0. Okay, now actually, once you put everything in this geometrical framework, okay, gamma n was what we all the constraints that we knew about the entropy function before. Okay, and then now I define this region called gamma n star, which is the region of all possible entropy functions. It is, well, in the past, people have been, including myself, have been thinking that, okay, the basic inequalities are all the constraints on the entropy function, and everything that holds for the entropy function can be derived from these basic inequalities. But once you put things in this geometrical perspective, it becomes clear very immediately that it is not clear whether there's no gap between these two regions. Okay, what I mean is that it could very well be possible that gamma n star is strictly contained in the is a proper subset of the region gamma n. Okay, previously we thought that the two regions are the same, but once you put the two, well, there was no region at that point, but we are thinking that the basic inequalities are just complete. But once you put everything in this geometrical perspective, then you will naturally ask the question whether there's any gap between these two regions. Okay, now because of the this setup, we can immediately develop a program that can prove entropy inequalities automatically. So the let me see. Okay, so what happens is that if you look at this picture, so forget about the gamma n star for the time being. We just look at Shannon type inequalities. So let me cross this thing out for the time being. Now, if I have an inequality like this, okay, then it is a Shannon type inequality because this half space totally contains the region gamma n, okay? Whereas if it is the other situation, okay, like this, it cuts inside gamma n, okay? Then this is not a Shannon type inequality, okay? Now to check whether an inequality of this form is a Shannon type inequality or not, I'm not going to get into details, but it suffices to say that you can determine where one case from another case by solving a linear program. Okay. So because of this, we were able to come up with a software called ITIP, Information Theoretic Inequality Prover, with my Fomston Yeung. Okay. ITIP, that was back in 1996. With this, you can type in an inequality, and if it is a Shannon type inequality, it will come back and tell you that it is actually 1. If not, it will tell you that it cannot be proved using this technique. And then subsequently, there were different versions of it. In 2007, a bunch of researchers from EPFL, these are Suhas Degavi's group, and they came out with another version called XITIP. So what happened was that ITIP was originally written as a function in MATLAB. So you have to have MATLAB to run it. Whereas XITIP was written in C. And then in 2009, S.Y. Chung from KAIST in Korea came up with another approach to this problem, and he came up with a rule-based algorithm for determining whether an inequality is a Shannon type inequality or not. Okay, but I am not sure whether he has ever released this to the public. And most recently, with Chiwei Tan and Lin Ling and Siwei Ho, we came up with something called ITIP. Wow, it doesn't have a very intuitive name. We just call this automated information theoretic inequality prover. And ITIP is actually cloud-based, and we put it on the web, and everybody can just access this software without installing anything, right, on your computer. You just go to the web, and you can input your inequalities, and it can prove it for you. And even better, it can actually provide a human readable proof. Okay, previously, for ITIP and other inequality prover, it just tells you whether it is Shannon type inequality or it is not. It cannot give you a human readable proof. So ITIP is actually quite useful. Not only that it gives you a human readable proof, but it can give you a shortest proof in some sense. Okay, so that if you input an inequality, it can give you a proof, and you can directly use this proof in your paper, for example. Okay, now Pippenger's problem can be rephrased in the following way. So Pippenger asks whether there exists any laws of information beyond the polymetroidal axioms or equivalently Shannon type inequalities. Okay, so based on this geometrical interpretation, another way to an equivalent way to phrase this problem is whether the closure of gamma n star is equal to gamma n. Okay, now the answer is no. If there exists an entropy inequality GH greater than or equal to 0, which cuts between gamma n and gamma n star. What I mean is that there's a gap between these two regions, and this gap is has a non-zero measure. Okay, such an inequality would be called a non-Shannon type inequality. So let me go to the next slide to show you the picture of this. So it would be something like this. Okay? If gamma n and gamma n star has a gap, then you can cut an inequality through, and that would be a non-Shannon type inequality. As I mentioned, once you put everything in this geometrical perspective, the possible existence of non-Shannon type inequalities is very clear. Okay, now the it is not difficult to show that gamma 2 star is equal to gamma 2 when there are two random variables. There's no surprise. When when there are three random variables, there's a little surprise, namely that gamma 3 star is not equal to gamma 3. It is strictly smaller. But if you take the closure of gamma 3 star, it becomes gamma 3. Okay. As I mentioned, this region, gamma n star, may not be closed. At least it is not closed by definition, and it turns out that it is not closed even for three random variables. So therefore, because gamma 3 star is equal to gamma 3, unconstrained non-Shannon type inequalities can exist only for 4 or more random variables. Okay, now so in general, I just want to mention that in general, gamma n star is neither closed nor convex, but gamma n star is a convex cone. Okay, now I mentioned at the beginning that when I first introduced this geometrical framework, it is extremely important to pin down a value of n. So you can take n to be 2, 3, 4, 5, so on and so forth. But you cannot leave n indefinite, because if you leave n indefinite, then the entropy space would be like an infinite dimensional space, and there's very little that you can do about it. Things becomes extremely difficult. Okay, so I came up with this problem, and during this time, my close collaborator Zheng Zhang, we also he also obtained his PhD from my advisor, Professor Toby Berger, but I didn't know him until 1989, 1 year after I graduated. We didn't overlap at Cornell. Okay, so I worked with Zheng Zhang, who is a math wizard, and it was mainly due to his credit that we were able to discover the first unconstrained non-Shannon type inequality in 1998 for 4 random variables. So it may not make too much sense for me to talk about this inequality, but I would like to show this picture. Okay, so this is the 4-dimensional entropy space, and this is gamma 4 star, and this is gamma 4. So there's in fact a gap, and this inequality, now commonly known as Yeung inequality 98, actually cuts through this gap. Okay. So this is what this non-Shannon type inequality is about. So with this discovery, we then know that the previous known constraints on the entropy function, namely the basic inequalities or the polymetric axioms or the Shannon type inequalities, these constraints are not complete. There's something beyond that. Okay, and subsequently, ZY98 has been further generalized by various authors. Okay, and in particular, in this work by Matush in 2007, he showed that this region gamma, actually he showed that it was gamma 4 star, but because it holds for n equals 4, it holds for any larger n, right? Gamma n star in general is not a polytope, and hence there exists an infinite number of linear non-Shannon type inequalities. Okay, so so after we discovered this non-Shannon type inequality ZY98, and we were still not sure whether it is something very peculiar, very special, right? Or very peculiar. But in fact, there exists not just one non-Shannon type inequality, but an infinite number of them, even for 4 random variables. So there are actually a lot of things that we don't know about the entropy function. Okay, and so actually around that time, Doty, Freiling, and Ziegler had discovered several tens of non-Shannon type inequalities by a search on the supercomputer at UCSD. So what they basically did was that there was a certain technique involved in proving ZY98. Okay, that was invented by Zheng. Okay, as I mentioned, the discovery of ZY98 actually is mostly credited to Zheng. What my contribution was the following. Now, once in a while, he came up with an inequality that he claimed to be a non-Shannon type inequality, and then I plugged it into ITIP, and ITIP says that okay, it is a Shannon type inequality. Sorry, go back and try to find another one. So there was a one time he came up with an inequality that he claimed to be non-Shannon type. I checked the proof 3 times. I didn't find anything wrong. But then I checked the proof the 4th time. I found that he made a very subtle mistake. So at the end it also failed. Okay, so that's basically my contribution toward the discovery of this inequality. So in the proving Z198, there's a technique called the copying lemma, right? The copy lemma, and then basically what Doty, Freiling, and Ziegler did was to incorporate ITIP and the copy lemma and run it on a supercomputer and try to search for new inequalities. And Ken Ziegler told me that on average it took about 1 week for the supercomputer to discover one new inequality. So it was really amazing that Zheng was able to find one by hand within 1.5 years, and even with a supercomputer, if you don't have the copy lemma, you won't be able to find new inequalities. And by far, this is still the only technique that can prove or discover a non-Shannon type inequality. Okay, in the second part of my talk, I'm going to explain the relation between this region gamma n star and many other fields in information sciences and also in mathematics. These include these four fields on the top. Okay, and the red arrow is a two-ended arrow. And it means that there's a one-to-one correspondence between these inequalities in this and inequalities in this. And these include Kolmogorov complexity, group theory, network coding, and a certain combinatorial structure. Okay? And this region gamma n star also has implication on probability theory, matrix theory, and even quantum mechanics. So it is, in fact, something of fundamental importance. So first, I talk about a very peculiar combinatorial structure, okay, which I coined the name quasi-uniform array. Now, the idea is that for a distribution Px, a sequence X of length n is strongly typical if the empirical distribution of X is approximately equal to Px, which means that the relative frequencies of the symbols in the alphabet set is approximately equal to the true probability. Okay. And then we consider the joint distribution Pxy, and then accordingly we can define typical sequences with respect to the joint distribution Pxy, with respect to the marginal distribution Px and the marginal distribution Py. And this can be illustrated by means of a two-dimensional quasi-uniform array. Why is it called a quasi-uniform array? I'm going to explain this in a moment. So for the time being, you just think of this as an array. Okay, now in this array, all the rows are indexed by the typical X sequences, and all the columns are indexed by the typical Y sequences. And the number of rows is approximately 2 to the power n times entropy of X, and then the number of columns is approximately equal to 2 to the power n times entropy of Y. Okay. Now, if a certain typical X sequence and a typical Y sequence, we put them together and they form a jointly typical pair, then we put a dot here. Okay, so it means that this typical X sequence and this typical Y sequence are jointly typical with each other, and the this array contains all such dots. Okay, now the reason why there are 2 to the power n times entropy of X typical X sequences is a result from the asymptotic equipartition property in information theory. Same thing for this one, and again apply the AEP, the asymptotic equipartition property. The total number of jointly typical pairs is approximately 2 to the power n times the joint entropy of X and Y. Okay, and so I just reproduced the picture here, and because we are using the notion of strong typicality, it can further be shown that for each row, the number of dots is approximately equal to 2 to the power n times entropy of Y given X. Okay, so this is the conditional entropy of Y given X, and likewise, each column has approximately the same number of dots, and the number of dots is approximately equal to 2 to the power n times the entropy of X given Y. Okay, so this is without getting into the details, this is an array that has a very peculiar structure. If you look at each row has the number of dots in different locations, but the number of dots on each row is approximately the same. You look at the columns, the same thing. The number of dots in each column is approximately the same. Okay, so with a very simple counting, okay, the total number of dots is 2 to the power n times entropy of X comma Y, and certainly this is less than or equal to the number of rows multiplied by the number of columns. So this becomes so it's upper bounded by 2 to the power n times entropy of X times 2 to the power n times entropy of Y. And if you take the logarithm and then you divide by n, you immediately get entropy of X comma Y is less than or equal to entropy of X plus entropy of Y, and which is the same as the basic inequality IXY is greater than or equal to 0. Okay, so this is so if you examine this inequality, right? Where's the gap? The gap actually corresponds to all these unfilled spaces in the array. Okay. Right, so this is a very physical interpretation of the inequality IXY is greater than or equal to 0. Okay. The same theme can be extended to 3 random variables where we have a quasi-uniform array, three-dimensional quasi-uniform array. So it is like a box. And then if you look at every cross-section, it has, in this direction, it has approximately the same number of dots. If you poke through the this box in this direction, and you find that every column would have approximately the same number of dots. Okay. All right. So for an n-dimensional quasi-uniform array, if now we assign a probability distribution to it, we assign equal probability to every one of the dots. Okay, it's uniformly distributed among all the dots. Then the projection on every lower dimensional plane has a uniform distribution over its support. Okay, there's something not difficult to see. And so we have seen that by applying a quasi-uniform array, we can prove that IXY is greater than or equal to 0. And actually, in the same way, we can prove all the basic inequalities. But the question is whether these quasi-uniform arrays fully capture all the constraints on the entropy function. Okay. That is whether every possible inequalities, including non-Shannon type inequality, can be fished out by these quasi-uniform arrays. Now, the answer turns out to be yes, and it was proved by Terence Chen, my former PhD student. Actually, this was in his master thesis. He showed that all constraints on the entropy function can be obtained through quasi-uniform arrays and vice versa. Okay, another field which has very intimate relation with entropy is group theory. Okay, this is a result by Terence Chen and myself in 1999. Actually, also in his in the Terence Chen's master thesis. So we consider a finite group G and subgroups G1, G2 up to Gn. Okay, and if you take the intersection of Gii in some sub indices alpha, we denote this by G alpha. Evidently, G alpha is also a subgroup. Now, a probability distribution, it can be shown that this is true. A probability distribution for n random variables, x1 of xn, can be constructed from any finite group and subgroups G1, G2 up to Gn, basically using a quasi-uniform array that I'm going to mention. Okay, if you use there's a certain construction that we use. Okay? Based on groups and subgroups, and with this construction, the entropy of x alpha is equal to it can be evaluated explicitly, and it's equal to log of the order of G divided by the order of G alpha. Okay. Now, because this is you can substitute these joint entropies. I mean, I'm talking about this and these entropies. So this is a special construction. Okay, so if you construct this, and then so this is a special form of the joint entropies, because all these inequalities that always holds for every possible probability distribution. In particular, those distributions constructed by groups and subgroups. You can substitute these inequalities and obtain inequalities concerning the orders of groups and subgroups. For example, we know that this inequality holds for all joint distributions. In particular, those distributions constructed from any finite group G and subgroups G1 and G2. Okay? So we replace this entropy by this, replace this by this, and replace this entropy by this. Okay? So the rule is that when you see H, you replace this by log, and then you have a fraction here. Upstairs, you have the order of G. Downstairs, you see x1, you replace this by order of G1. Same thing for entropy of x2. And for this one, we have log. Upstairs, we have the order of G. And then downstairs, because this x1, x2, we replace this by the order of G1 intersect G2. Okay, and then after eliminating all the logs, okay, we came up with this inequality, and this inequality governs the order of any finite group and subgroups G1 and G2. Okay, so you can do the same thing for any inequality that you know, which holds for every joint distributions, in particular non-Shannon type inequalities. So starting from Z198, which can be written in terms of all these unconditional joint entropies, we can obtain this, okay, something like this. Okay, but it is quite complicated and it's not clear what it means in group theory, but it's seemingly very fundamental. Okay, and it can be proved that the correspondence between entropy inequalities and group inequalities is 1-to-1, which means that if you, okay, you know that this holds, and then you can obtain this. If in a group theory domain you can somehow prove an inequality like this, then through the reverse symbolic substitution, you can obtain an entropy inequality. Okay, so this is a 1-to-1 correspondence. Okay, now what's the relation between finite group and quasi-uniform array? So it turns out that the distribution of the elements of a finite group among its subgroups exhibits what I call the quasi-uniform structure. So this is illustrated by this picture here. So we have so these are the dots are the group elements, okay, and G1 has is a subgroup and G2 is another subgroup, okay. So the subgroup G1 consists of these, okay, and the subgroup G2 consists of these. Okay, and the intersection between G1 and G2 is denoted by G12, and it contains these 3 dots. So you see that this is almost like a quasi-uniform array if you ignore the fact that every entry can have either 0 or 3 dots. Okay, so if you look at every one of these columns, there are 2 entries that are occupied. Okay, and 2 entries occupied, 2 entries occupied, and 2 entries occupied. If you look at the rows, each row again has the same number of dots being occupied. This one has 2 entries occupied, 2 entries occupied, and 2 entries occupied. The only difference between this array and a quasi-uniform array is that in a quasi-uniform array, each entry can have either 1 dot or 0 dot. But here it can have either 0 dots or a constant number of dots. Okay, so another subject that I would like to discuss is Kolmogorov complexity. And so this is a relation between entropy and Kolmogorov complexity. So we let K denotes the Kolmogorov complexity of a collection of sequences. And this paper written in 2000, published in 2000 by Hammer et al. There are actually 4 authors in it, and I know 2 of them are students of Kolmogorov, and the others may be their students. I don't know exactly. And they show that there exists a 1-to-1 correspondence between entropy inequalities and Kolmogorov complexity inequalities. For example, we know that this holds for every random variable x1 and x2, and this holds for any 2 sequences x and y. So entropy of x1 corresponds to the Kolmogorov complexity of a sequence x1, and so on and so forth. So here you just substitute the random variable by a sequence, and you substitute entropy by the Kolmogorov complexity. And again, this is a 1-to-1 correspondence, which means that if you can discover new inequalities in the Kolmogorov complexity domain, it can be translated into new inequalities in the entropy domain. So likewise, non-Shannon type Kolmogorov complexity inequalities can be obtained in this fashion. And so the next subject that I would like to talk about is probability theory. And in particular, I would like to talk about the problem of so-called compatibility of conditional independence. Now, this problem is sometimes called the implication problem. So the problem is the following. We are given a set of conditional independencies, and we want to know whether it implies a certain conditional independence. Okay, for example, we know that for 3 random variables following a Markov chain x1, x, y, and z in this order, and such that x and y are independent, then we can show that x and z are also independent. Okay, like this. So this is one instance of the implication problem. So this is a very basic problem in probability theory. But when I first got to know about this problem, I thought that this problem must have been solved 50 years ago, because the formulation is so simple, and turns out to be extremely hard for n greater than or equal to 4. So now this actually turns out to be a sub-problem of characterizing the region gamma n star, because a conditional independence relation is just a hyperplane in the entropy space. Specifically, from information theory, we know that if the mutual information between x and y conditioning on z is equal to 0, it is equivalent to x conditioning on x independent of y conditioning on z. Okay. Now x, y given z is equal to 0, as I mentioned before. x, y is actually x, z plus y, z minus entropy of x, y, z minus entropy of z equals 0. Okay, and just set this to 0, and this is nothing but a hyperplane in the entropy space. So this is actually can be regarded as a discrete problem embedded in a continuous problem. And namely, if you have a complete characterization of gamma n star, then you can settle this problem. So the problem n equals 4 was actually settled by Matouche, the same guy that proved that there exists an infinite number of non-Shannon type inequality. He actually settled this problem with the help of the following non-Shannon type inequality, okay, which is not one that exactly one that Zheng Zhang and I discovered. I mentioned ZY98, which is the unconstrained non-Shannon type inequality, and previously we also discovered a constrained non-Shannon type inequality, which is often called ZY97. This one is not one of these, but the form is the same as ZY98, ZY97, the constrained non-Shannon type inequality, except that the conditions are different. Okay, so with such a non-Shannon type inequality, Matouche was able to settle the problem, the implication problem for random variables, actually in a more general form, which I won't take time to explain right here. Okay, another relation is with matrix theory. So along this line, I need to introduce the differential entropy for a continuous distribution. So let X be a continuous random variable, and the differential entropy, assuming that the PDF exists, then the differential entropy is given by minus the integral of fx log fx dx. Okay, and the joint differential entropy can be defined accordingly. And Terence Chen in 2006 showed that a differential entropy is valid if and only if the coefficients of the random variables are balanced. Okay, and there are two conditions. Okay, first, it is a balanced inequality, which I'm going to explain to you, and the second condition is that its discrete counterpart is valid. So I'm going to give you an example on that. All right, so we want to see whether differential entropy of x given y is greater than or equal to 0. So what we first do is to express this in terms of the unconditional differential entropies, namely entropy of x comma y minus entropy of y. So now here we count the number of random variables here. The number of random variables is equal to 2, okay? And the number of random variable is equal to 1. So we collect all these coefficients and we have a 2 minus 1, which is equal to 1, and this is not equal to 0. So in this sense, we say that this inequality is not balanced. Okay, because it's not balanced, there's no chance that this inequality can hold. Okay. Now, whereas on the other hand, if we look at another another candidate inequality, ixy greater than or equal to 0. Okay, so ixy, so the count here is 1, the count here is 1, the count here is 2. So 1 plus 1 minus 2 is equal to 0, and therefore this inequality is balanced. And well, so it satisfies the first condition, and the second condition is that discrete counterpart always holds. The discrete counterpart is this: entropy of x plus entropy of y plus minus entropy of xy is greater than or equal to 0. So we know that this is true, and so this is a valid inequality even when the two random variables x and y are continuous. Okay. So so this just gives you a very simple example for what it means by a balanced inequalities. So this gives you a way of characterizing all constraints on differential entropy, which means that if you know all the constraints on the discrete entropies, then you also can know all the constraints on the differential entropy. Okay, now we consider a Gaussian distribution that a Gaussian vector. Okay, a Gaussian vector is defined by any symmetric positive definite matrix. Okay, because any such matrix is a valid covariance matrix, and so it defines the joint entropy of a Gaussian random vector. So you use this as the covariance matrix of the Gaussian distribution, and accordingly, the differential entropy of this Gaussian vector is equal to 1/2 log 2 pi e to the power n times the determinant of the covariance matrix, and then for any subset alpha of the index set, and a differential entropy of x sub alpha is equal to 1/2 log 2 pi e to the power the order of alpha, and multiplied by the determinant of k alpha, where k alpha is the corresponding submatrix of k. So you have k like this, and then alpha is a subset. You just pick the corresponding rows and columns. Okay, and this forms a submatrix which is called the principal minor. Okay, so we suppose we have a differential entropy inequality that we know is true for always. For example, this is the independence bound. So the differential entropy of x1, x2 up to xn is less than or equal to the summation of the differential entropy of the individual random variables. So if you substitute so this holds for every joint distribution, in particular the Gaussian distribution. So if you substitute in the Gaussian distribution and eliminate all these terms, you end up getting the Hadamard inequality, which says that for every symmetric positive definite matrix, the determinant is less than or equal to the product of the diagonal elements. So you can apply the same trick, and you plug in well, it turns out that's the CY98 non-Chen type inequality is a it's a balanced inequality, and so is the differential entropy version of it also holds. So you can substitute the Gaussian distributions to it and obtain this inequality, okay, which governs these determinants of the submatrices of the positive definite matrix. So again, there are a lot of things that are yet to be explored. Okay, so you can apply this to any non-Shannon type inequalities, and then you can obtain what I call non-Shannon type determinant inequalities. Okay, network coding is another very big subject, and so I would like to give a very simple illustration of a network coding example. So suppose in a network we generate a bit B1 on the left-hand side and we generate a bit B2 on the right-hand side, and we need to exchange the 2 bits across the network. And it is assumed that on each link you can only transmit 1 bit. So the usual way to think of the problem is that, okay, I have 2 tasks to deal with. The first task is to move B1 from left to right, and the second task is to move B2 from right to left. So if you want to move B1 from left to right, this is the only solution. Okay, there's basically only one route. And if you move B2 from right to left, this is the only solution. Okay. However, we find that there's a traffic jam here because we cannot send 2 bits through this link simultaneously. So if you stick with the usual routing paradigm or store forward paradigm, it's not going to work. Rather, if we apply a very simple coding inside a network like this, you send B1 up as you send B2 up, and then at this node you compute the binary sum of B1 and B2, which basically tells you whether B1 is equal to B2 or not. Okay, and then you send 1 copy of this to here and 1 copy of this to here. Now, on the right-hand side, this node knows its own bit B2, and what you can do is to is this. So you add, so B1 plus B2 is the receive bit, and then you add to this B2, and this is equal to B1 plus B2 plus B2. Okay, this is equal to B1 plus B2 must be equal to 0. Okay, so this B1 plus 0 and this is equal to B1. So you can determine B1 accordingly, and in the same fashion, the node on the right-hand side, based on its own bit B1 and also this binary sum, can determine the other bit B2. Okay, so all in all, this example shows that information is not a commodity. Okay? It's not a commodity flow problem. Okay? Although we have been, for the past several decades, we have been thinking along this way. Now, in general, network coding is required to achieve bandwidth optimality. So this is what network coding is about. It's about applying coding within the network. Okay, so what's the relation between entropy and network coding? Now, I won't get into the details. Now, for single source network coding, which means that you have only one information source to transmit, the network capacity is completely characterized by the maximum flows in the network. Now, however, when there are multiple sources in the network, the problem becomes much more tougher, and the problem has been studied by Zheng and myself, and also Ning Cai, Professor Cai, now also in Shanghai Tech, and also my close collaborator, and so this one is Zheng and his student. Okay, we finally obtained a complete characterization of the network capacity in terms of gamma n star. Okay, and this is an implicit characterization because we cannot determine gamma n star explicitly. And in 2007, Doherty, Froehlich, and Ziegler constructed the first multi-source network coding problem whose characterization of the network capacity requires Z1 and 8. So it gives an application of this non-Shannon type inequality that we discovered. And the construction is based on the Varmosh matroid in matroid theory. So matroid theory also comes into the picture. So, and Chen, which is the same Terence Chen and Alex Grant, in 2007 proved a one-to-one correspondence between entropy functions and multi-source network coding problems, which means that, in particular, it showed that any non-Shannon type inequality that you can ever come up with, it is useful in some multi-source network coding problems. So it has a one-to-one correspondence in this sense. Okay, so so that's why there's a one-to-one correspondence between gamma n star and network coding problems. Okay, so and another problem that I would like to mention, I think I can finish in 3 minutes. Is it okay?
Yes.
Okay, so secret sharing in cryptography was introduced by Blake Lee and Shamir independendly, both in 1979. And I won't get into the fine details, but actually not recently, it's 2008 already, more than 10 years ago, has applied the non-Shannon type inequality Z198 to obtain a new law bound on in a secret sharing problem. Okay, and secret sharing can actually be regarded as a special case of secure network coding, which is a security model of network coding that I just introduced. And this model was introduced by Cai Ning and myself in 2002. Okay, finally, I would like to mention quantum mechanics. So the von Neumann entropy is an extension of the Shannon entropy to quantum mechanics, and for the von Neumann entropy, there's something called the subadditivity property. Okay, and you can think of it as analogous to the basic inequalities for the Shannon type inequalities. That is, all these constraints on the von Neumann entropy that were known for a long time. Okay. It was first proved by Lieb and Ruskai, 1973. And so inspired by the discovery of non-Shannon type inequalities, Pippinger, the same guy who asked whether there are laws of information theory beyond the basic inequalities, he came back to the problem and proved that for a three-party system, there exists no inequality for the von Neumann entropy beyond strong subadditivity. So no surprise, okay, for the three-party system. However, 2 years later, Linden and Winter discovered that for a four-party system, there are new constraints, okay, beyond the strong subadditivity for non-von Neumann entropy. Okay, so there's something new in this domain. Okay, so this picture again, I've shown you, it gives a quick summary of my talk, and so here comes the conclusion. Well, Imre Twister, a very famous information theorist and also a mathematician, advocates that information theory should be an integral part of mathematics. I totally agree. And it is clear that constraints on the entropy function has fundamental implications in a number of fields in information science, mathematics, and physics. And so there are a lot that are yet to be explored. And there exists, in particular, there exists one-to-one correspondence between the entropy function, group theory, Kolmogorov complexity, and network coding. If you can solve any one of them, you can solve the other problems too. So this suggests that they share the same underlying structure. So what is this underlying structure? In my opinion, this underlying structure is the quasi-uniform array. Okay? This is a very fundamental structure that's relevant in this context. And also, as I mentioned, matrix theory plays a role here and there, in particular in the study of conditional independence and network coding. So this concludes my talk. Yeah. So, okay, final remark. Non-Shannon type inequalities in different fields need further understanding. Our understanding is very, very small at this point. Okay, thank you very much.
谢谢杨老师。谢谢这个非常精彩的报告。大家有什么问题？或者我现在问一个问题，也许是，就我如果有一个向量，我想判断说它是不是这个 entropy vector， 或者说离这个伽马 n star 这个距离有多远？这个有什么办法吗？
这个没有什么好的办法。OK，
说就 n 很小的时候，是不是可能会有办法
？n 很小的时候，这个n 等于3的时候，我们就知道了 n 等于3那个 gamma 3 star 这个 closure 我们就知道这是等于 gamma 3。OK， 但是那个 n 等于4还是很多东西不知道。
OK，
我们有一个 inner bound， 可以有一个 inner bound， 但是那个 inner 也不一定是紧的。
这个 bound 是指它离这个伽马 n 或者伽马 n star 的距离吗？您说的这个？
不是，我说那个 inner bound。这个 gamma 4 star 的 inner bound， 就是这个 inner bound 里面东西，我们都知道它是 entropic 的。
OK，
我们有 outer bound 的，有 inner bound 的，是这个Z19A 就是有 outer bound， 但是它有多紧还是那个不确定。
OK， 是不是一般来说是 undecidable， 就是一般给个向量是没法判断的？
没错。
这是严格证明的结论是吗？我觉得这是证明的结论，就是说这个是
那个如果那个n 4个 random variable 不紧的话，那个我们知道这个它有一个 outer bound 有 inner bound， 这个 region 就是在 somewhere in between。 OK， 我们不知道它在哪里。总之这个 inner bound 跟 outer bound 是中间有一个 gap。那 n 等于4是这样的，n 等于大于等于4都是同样的。
我如果拿一个哪位在问问题？我再问一个问题，就是如果我拿一个球面，对吧？譬如单位球面和您讲的这个锥来一截，那么
是什么的？你可不可以再讲一次？
我现在拿一个单位的球面，那么和这个
单位球球面是英文是什么
？sphere， unit sphere。
unit sphere， OK，unit sphere，OK。在某一点有某一个点，那个有个 unit sphere。
你取的这个空间的原点嘛，就是说现在我想问，有没有估计这个它和这个锥的交出来这一块这个体积或者球面的这个侧度是多少？这有估计吗？
这个都没有什么好的答案。OK， 这个问题现在已经是非常困难了。现在还有一些那个我刚才说那个这个 gamma 4 star， 它的表面也是可以是很稀奇古怪的。OK， 它在里面都是那个实心的，但是那个在那个表面可能这 lower dimensional 的东西可以是非常稀奇古怪的。
它是不是一个可测题？可能都不知道是吗？它是可测的吗？
对，这个也不知道，这个也 not obvious。
还有最近他们很多人在做，把这个期望弄到非线性期望，就好像说因为这个随机变量这些事情就是线性的，这个取这个期望，那么国内那个彭石哥他们把它弄线性。